In a chemical reaction where we have reactant A and reactant B to form a product C, right? If we have an excessive amount of reactant A and a small amount of reactant B, right? If reactant B runs out, the leftover of reactant A will not have any more reactant B to react with, so it will just remain there without reaction, so it will not participate in forming product C. That means that reactant B is called the limiting reactant because it's the one that's limited in amount and it's the one that controls the reaction, while A is in excess because there's leftover after reactant B runs out. Okay, reactant B, because it's the limiting reactant, it's the one that determines the amount of product C, because if reactant B runs out, then reactant C will be formed according to the amount of reactant B, right? Because reactant A will be left over. Now let's take an example. 3 grams of magnesium was added to 12 grams of ethanoic acid. That's ethanoic acid. The mass of 1 mole of magnesium is 24 grams. The mass of 1 mole of acid is 60 grams. Which one, magnesium or ethanoic acid, is an excess, and show your work? Okay, there's a very simple way to determine which one is the limiting reactant. First of all, we have a relation between magnesium and ethanoic acid. The mole ratio is 1:2. We have 3 grams of magnesium and 12 grams of ethanoic acid. So let's calculate the number of moles for magnesium and the number of moles for ethanoic acid. The number of moles for magnesium will be equal to the mass divided by 24, which is the relative atomic mass for magnesium, which will be equal to 0.125 mole. Right? For ethanoic acid, we have 12 grams divided by the relative molecular mass for ethanoic acid, which is 2 multiplied by 12 plus 4 multiplied by 1, because we have 4 hydrogen atoms, 3 here and 1 here, and these are the 2 carbons, plus 2 multiplied by 16, because we have 2 oxygen atoms. That would be equal to 0.2 mole. We can't use these numbers to determine the limiting reactant. You can't just say that, okay, these are 0.12 moles, and that's 0.2, so that's less, so magnesium will be the limiting. No, that's incorrect. Right? There is one extra step that you need to take. Right? Let's just clear these. Here we have 0.2 and here we have 0.125. Divide each of these by the coefficient that's in the equation. For example, magnesium has a coefficient of 1, so divide here by 1. Ethanoic acid has a coefficient of 2, so divide here by 2, right? Now the answer will be 0.1, and here we'll have 0.125. Now you can compare these two numbers based on which one is larger. 0.1 is the smaller number, so ethanoic acid is the limiting reactant. You always have to refer to the equation while measuring the limiting reactant, right? So we calculated the number of moles of magnesium and ethanoic acid, then we divided by the coefficient of each of these reactants from the equation. The smaller number is the limiting reactant. Okay, so magnesium is in excess, or ethanoic acid is the limiting reactant, but in the question it's asking about the element that's in excess, so magnesium is in excess. How many moles of hydrogen were formed? Okay, which reactant are we gonna use to measure the amount of hydrogen? Of course we're gonna use the limiting reactant, which is ethanoic acid. So we're gonna make a relation between hydrogen and ethanoic acid. That's ethanoic acid, that's hydrogen. We have 2 moles from the equation that produce 1 mole of hydrogen. We have from the question 3 grams of magnesium and 12 grams of ethanoic acid. So that's the number, that's the mass. We're going to convert it to a number of moles. We've already done that right here. So we have 0.2 moles of ethanoic acid. How many moles of hydrogen is that going to form? Scissors way. Now the number of moles for hydrogen will be equal to 0.2 multiplied by 1 divided by 2, which is 0.1 mole. That's the answer. Calculate the volume of hydrogen formed. Okay, the volume equals the number of mole multiplied by 24. 0.1 multiplied by 24 equals 2.4 decimeter cube. Let's take another example. Always remember, you can just pause the video and answer it for yourself, and once you're done you can check the answer by replaying it. Calculate the mass of iron sulfide produced from the reaction between 28 grams of iron with 20 grams of sulfur. Okay, the mole ratio here is 1:1 from the equation. Now let's get the number of moles of iron and the number of moles of sulfur. Here we have mass for iron divided by the relative atomic mass of iron, which is 56. That will be equal to 0.5 mole. For sulfur, we have 20 divided by 32, which will be equal to 0.625. Now the next step is to divide the number of moles we've just gotten by the coefficient. Now we have 0.5 for iron divided by 1 and 0.625 divided by 1. That tells us that iron is the limiting reactant because 0.5 is less than 0.625, right? Okay, now that we know the limiting reactant, we can use that information to calculate the mass of iron sulfide that's required in the question. Okay, so we're going to make a relation between the limiting reactant, that's iron, and iron sulfide, FeS, right? From the equation, the mole ratio is 1:1, and the FeS will be 0.5. Sorry, the iron has 0.5 moles. So scissors way, we're gonna get the number of moles for FeS, which will be equal to 0.5 mole. Now, the mass will be equal to the number of moles multiplied by the relative molecular mass for FeS, which will be equal to 44 grams. Calculate the mass of carbon dioxide produced from the reaction between 2 decimeter cube of ethene with 0.5 decimeter cube of oxygen. We need the mass of carbon dioxide. First of all, we need to write the balanced chemical equation. So we have C2H4 plus oxygen, which will give out carbon dioxide and water. A simple combustion reaction of hydrocarbon. Now let's balance the chemical equation. We start off by balancing carbon. Here we have 2 carbon atoms in the reactants and 1 carbon atom in the product, so here we add 2. Then the hydrogen. Here we have 4 hydrogen atoms in the reactants and 2 hydrogen atoms in the product, so we add another 2. Now to balancing the oxygen. In the reactant, we have 2 oxygen atoms, while in the product we have 2 multiplied by 2, that's 4 oxygen atoms, plus 2 more oxygen atoms, that's 6 oxygen atoms. So we add 3 right here. Now we have 6 oxygen atoms in the reactants and 6 oxygen atoms in the products. Now we need to determine our limiting reactant so that we can measure the mass of carbon dioxide according to that limiting reactant. The relation will be between ethene and oxygen. The ratio is 1:3. and we have 2 decimeter cube of C2H4. So we need to measure the number of moles for ethene. 2 decimeter cube divided by 24, because that's a gas, 0.083 mole. Now the number of moles for oxygen will be equal to 0.5 divided by 24, should be equal to 0.02. Now we place these numbers right here, and that one is for ethene, and then divide them by their coefficient. That's divided by 1, that one is divided by 3 from the balanced chemical equation. Right? That gives us 0.006 for oxygen and 0.083, meaning that oxygen is the limiting reactant. Okay, now we need to measure the mass of carbon dioxide based on knowing that oxygen is the limiting reactant. So the relation will be between oxygen and the carbon dioxide, using also the mole ratio from the equation. Now we have oxygen and carbon dioxide, so that's 3:2. We've measured the number of moles, 0.02, right here. Scissors way, we're gonna get the number of moles for carbon dioxide, which will be equal to 0.013 mole. Now we need the mass of carbon dioxide, which is the number of moles, multiplied by the relative molecular mass for carbon dioxide, multiplied by 16, which will be equal to 0.59 grams. The last thing we're going to talk about in this topic is the empirical formula and the molecular formula. To give you a bit of perspective on the empirical formula and the molecular formula, consider this following compound, C2H4. This formula tells us that we have 2 carbon atoms and 4 hydrogen atoms. There is actually a compound in nature that has this formula. It's called ethane, right? So we call this a molecular formula because it tells us the number, the actual number and type of atoms in a compound. Now, if we want to get the empirical formula from this compound, we need to get the simplest whole ratio between these 2 numbers. So the ratio will be 1:2, so that's CH2. Okay, just divided here by 2 and here by 2. Now this is the empirical formula. It shows us the simplest whole ratio of the compound. There is no actual compound in nature that has this formula. So this is an imaginary compound. There's no compound formed of 1 single carbon bonded to 2 hydrogen atoms. There's no such thing, right? So this is an imaginary compound, while this one, C2H4, is an actual real compound. The empirical and molecular formula is very common in organic chemistry, but it's so rare in inorganic chemistry. For example, or for a matter of fact, inorganic compounds do not have a molecular and empirical formula that they are the same. The molecular formula is the same as the empirical formula, except for some very scarce or rare compounds like hydrogen peroxide, for example. This is the actual compound. This is the molecular formula. If we want to convert it to an empirical formula, we'll get the simplest whole ratio, divide here by 2 and here by 2, so it's going to be HO. So this is a molecular formula, and this one is an empirical formula, right? Now to the definitions. Empirical formula shows the simplest whole number ratio of atoms present in the compound, and these are very important keywords. The molecular formula shows the number and type of atoms forming the molecule of the compound. For example, C6H6, that's a molecular formula because it's not simplified. If you simplify it, you get CH, which is an empirical formula. Again, this is a real compound, that's hexane. Again, that's a real compound, while this one is an imaginary compound. Organic compounds have both empirical and molecular formula. Most inorganic compounds, the empirical formula is the same as the molecular formula. Very few inorganic compounds have an empirical formula like hydrogen peroxide, which has an empirical formula of HO. Right? Now, let's take an example. A hydrocarbon contains 80% carbon. Find the empirical formula and the molecular formula if the real relative molecular mass of the compound is 30. Okay, so we have carbon and we have hydrogen. Consider that the mass of carbon is 80. That means that the mass of hydrogen will be 100 minus 80, which is 20. Right? Now, we divide by the relative atomic mass for each compound. So here we divide by 12, here we divide by 1. 80 divided by 12 equals 6.66, and here we have 20. Now we divide by the smallest number, that gives us 1:3. So the empirical formula is CH3. Now this is the empirical formula, right? Now let's get the molecular formula. First of all, we need to measure the relative molecular mass for the empirical formula. It will be equal to 12 plus 3 multiplied by 1, which will be equal to 50. Right? Now we need the number of moles. The number of moles will be equal to the mass, which is 30 divided by 15, which is the relative molecular mass that we got, which is 2. Now, to get the molecular formula, multiply this number of moles by that empirical formula. So, molecular formula will be equal to C2H6. 1 multiplied by 2 equals 2, 3 multiplied by 2 equals 6. So this is the molecular formula. Another example. A carbohydrate has 40% of its mass carbon, 6.66 hydrogen. Find the empirical M molecular formula given that its relative molecular mass is 180. So we have carbohydrate, which means that it's formed of carbon, hydrogen, and oxygen. We have 40% of that mass, carbon, 6.66 hydrogen, which means that we have 100 minus 40 plus 6.66 of oxygen, which is 53.34. Right? Now, divide each of these masses by the relative atomic mass for each respective element. 40 divided by 12, 6.66 divided by 1, 53.34 divided by 60. So we get the following ratio: 3.33 to 6.66 to 3.33. Right? Now we divide by the smallest number right here, okay, which is 3.33. From this, we get the following ratio, which is 1:1. So the formula is CH2O. Okay, so that's the empirical formula. Now we get the mass, the relative. So the empirical formula is CH2O. Now we get the relative molecular mass for this formula, which is 12 plus 2 multiplied by 1 plus 16, which equals 30 grams. Now we get the N number of moles, the mass, the actual mass, which is 180, divided by the relative molecular mass of the empirical formula, which will be equal to 6. Now, to get the molecular formula, multiply that n by the relative, by the empirical formula. So we have C6H, 2 multiplied by 6 is 12, O, 1 multiplied by 6 equals 6. So this is the molecular formula. Question number 33. Calculate the empirical formula of the formed compound from the reaction of 0.24 grams of magnesium with 0.16 grams of oxygen. So we have magnesium and oxygen. We're going to calculate the number of moles for magnesium, which is the mass divided by the relative atomic mass of magnesium, which is 0.01 mole. The same thing for oxygen. 0.16 divided by 16 should be equal to 0.01 mole. Right? Now, as we can notice that these two are the same number of moles. If we divide each of them by the same number, 0.01, we'll get a ratio of 1:1, meaning that the empirical formula for the compound is MgO, because the ratio is the same because the number of moles is the same. 34, 35, and 36 are the exact same idea, right? Let's take 38 as our last and final question. An excess of hydrochloric acid was added to 1.23 grams of barium carbonate. The volume of carbon dioxide collected was 0.120 decimeter cube. The impurities did not react with the acid. Calculate the percentage purity of the barium carbonate. The molar gas volume at RTP is 24 decimeter cube. The number of moles of carbon dioxide collected is, we collected 0.120 decimeter cube, so the number of moles will be the volume divided by 24, which equals 0.05. The number of moles of barium carbonate reacted. From the equation, we have BaCO3 reacting with or forming carbon dioxide. The mole ratio is 1:1. We have 0.005 mole of carbon dioxide. Scissors way, we get the number of moles for barium carbonate, which is 0.005 mole, right? Now, the mass of mole, 1 mole of barium carbonate, also called the relative molecular mass, is 137 plus 12 plus 3 multiplied by 16 should be equal to 197 grams. The mass of barium carbonate itself will be equal to the mass of the number of moles, which is 0.005. So the mass will be equal to the number of moles multiplied by the relative molecular mass, should be equal to 0.985 grams. The percentage purity of barium carbonate will be equal to the mass of barium carbonate divided by the actual mass or the given mass of barium carbonate, which is 1.23. Here we have 0.985 divided by 1.23 multiplied by 100 should be equal to 80.08%. The rest of the questions are like the same idea. You can answer them and you find the answers in the notes. Of course, you'll find the notes and the classified with the marking scheme on our Telegram group. You can access it from the link in the video description. Don't forget to subscribe to the channel. Thank you so much for watching, and I'll see you in the next video. Take care.